In this video, we are going to discuss on topic for a beam. If movement is coming, along with that torsion and shear force is also coming, then combination of this flexure, torsion and shear you have to design. So combination of these three, now subsequent clauses have been given in limit state of design. In clause number 41.3.1, page number 75, follows the criteria of design stipulations. Now you might have learned in strength of materials that if a member is subjected to torsion, the shear stresses are induced in the structure. So when a beam is subjected to a torsion, more or less we have to ensure that the beam has sufficient shear capacity. So here we have a small problem which I would like to dictate for you or solve it for you. A reinforced concrete beam has the following data. Width of section 300 mm. Depth of section 500 mm. Here it is said that is a depth of section. It didn't mention overall depth or it is effective depth. So because it is not given, you can consider it as your overall depth. Depth of section 500 mm. Factored bending moment 80 kilonewton meter. Factored torsional moment 40 kilonewton meter. Factored torsional moment 40 kilonewton meter. Factored shear force 70 kilonewton. Take M15 grade concrete and Fe415 grade steel. So first write down the given data in the solution part. Width of section is given to you, factored moment Mu is given to you, torsional moment that is Mt is given to you, and factored shear force that is Vu is given to you. You are also given with overall depth of section. You need to calculate the effective depth of the section. Okay, so effective depth of the section we have discussed in the previous class that you can calculate effective depth of the section by deducting the d dash from the overall depth. D dash is the center of the reinforcement to the bottommost fiber of the beam is called as d dash. So from overall capital D, if you deduct d dash, then you will get small d dash. So that is first objective you need to calculate. So let us start the problem. So effective depth is given by small d is given by overall depth minus d dash. Fine. Now overall depth is given as 500 mm. Now this can be calculated as d equals to 500 minus clear cover is 25 mm plus I am calculating the d dash, right? 25 mm plus full diameter of stirrup full diameter of stirrup I have taken as 10, 8, and let me take 10. Last time I have taken 8, I am taking 10 now. Then the main diameter half you have to take. Let us take main diameter as 40. So 40 by 2. Now you can calculate D from here as 455 mm. So diameter assumed as a 20 mm. Fine. Now you are supposed to calculate first equivalent shear. VE. Now this VE is given in clause number 41.3.1 in page 75. Right. So referring this, now equivalent shear VE can be written as VU plus 1.6 times ultimate torsional moment divided by breadth of beam. Now VU is given as 70 kilonewton plus 1.6 times TU is given as ultimate moment is given as 40 kilonewton meter, and breadth of beam for our system is 300 mm. In meters it is 0.3. So this will give you a value of 283.33 kilonewton. Now, when you know VE, you can calculate the nominal shear stress. Nominal shear stress tau VE as VE divided by V times D. VE is 283.33 into 10 power 3 divided by V is 300 into D is 455. This will give you a value of 2.07 Newton per mm square. Right. Next. Now, if you want to calculate longitudinal reinforcement, this is helpful in calculation of shear reinforcement that is stirrup. And if you want to calculate the pressure reinforcement, then you need to calculate the equivalent moment, because you are having torsional moment along with the flexure moment. So the equivalent moment ME, one is given as MU plus MT. This is again drawn, stipulated in clause number 41.4.2 in page number same 75. So this ME1 is given by MU. So MU is given as, ultimate moment is given as 80 kilonewton meter in the given question, and MT can be calculated as TU into 1 plus D by B divided by 1.7. Now TU is given as 40, 1 plus 0.5 by 0.3 divided by 1.7. Now this moment is given as 162.745. Now you need to compare these two, right, in the subsequent clause, because in the same clause 41.4.2, if you read out after this equation, if MT is greater than MU, then you need to calculate ME2. I repeat, if MT is greater than MU, then you need to calculate MU2, where you need to allot that moment for compression reinforcement. This movement is allotted for tensile reinforcement and MU2 is allotted for compression reinforcement, which is clearly said in the subsequent clause. If you read out it, you can get it. For our case, MT is less than MU, so it is fine that we can go with MU1. There is no MU2 there. Okay. Now, assuming the section as under reinforced section, we can now calculate the reinforcement required. So MU2 ME1 is given by 80 plus 62.745, which gives a value of 142.745 kilonewton meter. For this movement, you need to calculate the steel requirement. So assuming the section as under reinforced section, now equating moment of resistance with ultimate moment which is coming ME1, then MR, and equating ME1 equals to MR equals to 0.87 Fi AST into D minus 0.42 XC. Right? There is also another equation which is in the code. That equation is this equation 4 of the exam. So in this, XU is given by 0.87 Fi AST into divided by 0.36 FCKB. Now back substituting, first calculate this. So this is given by 0.87 into 415 into AST, we need to calculate it, divided by 0.36. FCK is 20, breadth is 300. Now you will get some value in terms of AST. Now back substitute this equation here, right? So ME1 is given by 142.475, 142.745 into 10 power 6 equals to 0.87 into 415 into AST into D is 455 minus 0.42. From here you substitute the value AST, right? If you solve this equation, you will get AST value, right? So I am taking approximately this value. So I did not calculate it here the XU value. You calculate the XU value, right? This value in terms of AST you get, and back substitute this value in this equation, you will get AST. But I have taken some value for rubber conservation. So number of bars can be calculated as AST required, by AST assume AST required is 979.94. Now AST assumed, you can assume every dia. I am here assuming as 20 mm. So here pi by 4 into 20 square. Now this much is required and each of the bar is 20 mm. So cross extend this. So you will get approximately 4 numbers. So write down statement here. Provide 4 numbers 20 mm dia HYST bars at tension. And now you cannot just provide 4 numbers bottom, you need to provide some kind of hanger bars at top side also, right? So let us provide 2 bars of, so there are 4, right? So it is provide 3 numbers of 12 mm dia HYST bars at compression as hanger bars. So I have not designed for this, right? This is based on the experience. Now you can take any value. Oh, I have taken how much? I have taken 3 of 12. You can take 3 of 16 also, but 16 if I take more, weight will come. So again it will become more reinforced section, right? You can take 4 numbers of 10 mm. That's okay, no problem, because you are telling here 4. It's your requirement. Now after writing here, now you have completed the steel requirement. So our beam now looks something like this. Now we got a beam of depth 500 and breadth as 300, if I am not wrong. Yeah, breadth as 300. Now you have provided 3 numbers of 12 mm, 1, 2 and 3. So 3 of 12 dia. Now at bottom you have to provide 4 of 20 dia. 1, 2, 3 and 4. 4 of 20 dia. Now you need to design the shear reinforcement. Shear reinforcement we have discussed. It will be a ring, right? This is how it goes. Now you need to calculate that shear reinforcement. Put side heading. You have calculated equivalent shear here, tau V here. Now design for shear is Torsion. Design of shear reinforcement. Now design and shear reinforcement we have discussed. We need to calculate design strength of concrete. Design strength of concrete, that is tau C you need to calculate, and this tau C should be compared with tau V, right? Now this is tau V we have got here. Now tau C depends upon 2 things, that is percentage reinforcement provided divided by and grade of concrete. Fine. Now you need to calculate percentage of steel, PT %. is given by area of steel provided is 4 numbers of 20. 4 numbers of 20 divided by BD. What is B? B is 300, D is 455 into 100. You will approximately get this value around 0.7. I may be wrong, please verify. And the grade of concrete you are given with grade of concrete you are given as M15. So you need to look in table number 19, right? And for 0.71 you need to interpolate the values which are given in the M15 grade concrete. So it is in between 0.46 and 0.54. So interpolation values will be 0.46 plus 0.54 minus 0.46 divided by 0.75 minus 0.50 into 0.71 minus 0.50. So you recall whatever we have discussed about how this interpolation has been done. So if you solve this, then tau C value you can evaluate as 0.527 Newton per mm square. Now your shear strength of concrete, right? Shear strength of concrete is how much? 0.527. But as per the given loading, how much you are getting is you need to compare with, right? So, but from the loading it is 2, but your concrete is taking only 0.527. So shear reinforcement design we have to do it. Okay. But shear reinforcement for the beam where the torsional movement, shear and bending moment is coming, shear reinforcement design is difficult. In the same clause, the 40 is stipulated that shear reinforcement can be designed as, so before that as, you have to compare, right? Tau V is greater than tau C. Shear reinforcement is designed. Shall be designed. Now this shear reinforcement in the same code book it is given that ASV can be calculated as TUSV by B1 D1 into 0.87 Fy plus VU into SV divided by 2.5 D1 into 0.87 F1. Now, what is ASV is number of area of shear reinforcement. For example, now if you cut this section here, if I cut this section here, how many legs we are cutting here? Now we are cutting here is 2 legs. So 2 times the cross section of one, how many cross section that the ASV is nothing but area of the cross section you have touched. So here we have 2 pi by 4. If you assume 10 mm, you have to take 10 mm. Not, you have assumed not more. So we will do that. So you have got DU, VU, SV. You need to calculate ASV. You can assume 8 mm or 10 mm. Now here we have assumed as 10 mm. So we will take 10 mm. Then what is this B1 and D1? Now, as per the statement, from here to here is V1. Right? And from center to this center is D1. Now, you are supposed to calculate this B1, D1, right? And substitute it there in order to get the spacing of shear, right? So B1 is given by, Now total is 300. We have got total is 300. 300. Now from 300 you need to deduct 2 side covers, right? Minus 2 side covers is 25. After deducting 2 side covers, you have to deduct 2 stirrup dia. Stirrup dia I have taken as 10. Then I have to deduct here one time, here one time. That is 2 times half of main dia. Main dia is 1. Now this value you can calculate as 210 mm. Now D1, similarly D1 is given as 500 minus 2 times of top cover and bottom cover minus 2 times stirrup minus half of 20 dia at bottom minus half of, how much is that? 12 dia at top. And if you supposed to calculate this, you will get as 414 mm. Now I am assuming 2-legged stirrup of 10 mm dia. So this will become 2 times pi by 4 into 10 square, because I have assumed two-legged 10 mm dia stirrup. So equals to TU. TU is 40 kilonewton meter. We are taking in mm, so you have to convert it 40 into 10 power 6. SV we need to calculate. Divided by B1 D1. B1 is 210. D1 is 414. D1 is 210. D1 is 414. And 0.87 into Fy. Fy how much? 415, right? Fy is 415. Plus shear Vu only. Vu is 70. So 70 into 10 power 3 because it is in kilonewtons into SV divided by 2.5 D1. 2.5 D1 is 414 into 0.87 415. From this whole equation, you have to calculate spacing SV, and it may come around 107 mm approximately. So let us take it as 100 mm center to center. So when you have decided that the dia of 10 mm, if you take two-legged stirrup, you are getting 100 mm. If you think that this 100 mm is very small, then you can go for 4-legged 10 mm. This will become 4 and this will become 200 spacing. And if you want to increase the dia, you can go for 2-legged 12 mm dia. 12 mm dia normally we will not follow for stirrup, either 8 or either 10, right? So if you are taking 12 mm dia stirrup, then you have to increase this to 16 mm. So here you make a comment, provide 10 mm, two-legged 10 mm dia at the rate 100 mm center to center as shear reinforcement. When you have completed this statement, immediately write down here that this is 10 dia at the rate 100 mm C to C. So that is this beam is good enough to carry the movement, ultimate shear force and torsion movement combined together. Now take some more problems from your side. Now practice it and take a look from your own side, change these values, and so that you are ready for your final.